All right, ladies and gentlemen, this is going to be the lecture about electrolysis, which is our final topic, not just in electrochemistry, but in the new material for the year. So this is actually kind of exciting. This is the final topic from Chapter 20 from the Electrochem chapter. And you should make sure that you have in front of you your the page that has the slides about electrolysis. It should have this sentence on it, as well as your sample problems from lecture. We're going to be doing the last two together, and I am going to be talking about something on the reference table as well, so make sure that's out. Electrolysis. You might remember from Regents Chem, hopefully at least you remember the word, but electrolysis is in many ways the opposite of a voltaic cell. Electrolysis is where you use electricity to cause a non-spontaneous chemical reaction to occur. A voltaic cell is where you have a spontaneous redox reaction that produces electricity. It makes volts. You can use it to power something else. That's a voltaic cell. Electrolysis is the opposite. It is saying, we've got this reaction that doesn't happen on its own. How can we get it to happen? Why don't we shoot some electricity through it and force it to occur? That's an electrolytic cell. And up here, the two pictures that are here are two examples of electrolytic cells. The first one, the yellow one here, notice this. We're putting sodium chloride in. So we're taking NaCl and we're turning it into, if you look at what's happening, what's coming out, liquid sodium is coming out and chlorine gas is coming out, balancing it like that. This reaction, taking sodium chloride and turning it into liquid sodium and chlorine gas, is very, very much a non-spontaneous reaction. This reaction doesn't happen on its own, and quite frankly, it's a good thing that this reaction doesn't happen on its own, because then otherwise all of our table salt at home would be randomly turning into a metal that lights on fire when it comes into contact with water, and a highly toxic, highly poisonous gas. So yeah, this reaction doesn't happen on its own, but let's say you want to generate this, very reactive metal, and you want to generate this very toxic gas. Sodium chloride is going to be your obvious choice for these elements, but you have to force it to happen. Hence the electrolytic cell, the cell that uses electrical energy to cause something to occur. On the right side, we have a simpler example of an electrolytic cell, and notice that we still have a couple things I want to point about this figure. We still have an anode, which is still oxidation. It's the same reaction, by the way, for both of them. Both of them are involving sodium chloride and turning sodium chloride into chlorine gas and sodium metal. We still have reduction, and we still have a cathode. Electrons are still flowing from the anode to the cathode, so that is very much the same. But, difference, we have a battery. A battery here in place of a voltmeter, and that battery is providing the electricity that is causing this non-spontaneous reaction to occur. The battery is the thing that is forcing this to happen. It's saying it wouldn't happen on its own. We hook it up to a battery. The battery sort of jolts it and forces this redox reaction to happen. In the voltaic cell, not electrolytic, your anode is your negative electrode and your cathode is your positive electrode, and your voltmeter measures the spontaneous flow of electrons. That's what it's there for, if it's there at all. In electrolysis, however, the voltmeter gets replaced by a battery. No longer a voltmeter, now we have a battery instead. And your voltage source is, instead of simply measuring electron flow, instead of measuring just the flow of electrons that's happening spontaneously on its own, the battery has to be there to forcibly pump electrons. The electrons aren't going to move it on its own. Your voltage source, your battery, is forcing that to happen. The way that works, the way that the battery works in an electrolytic cell, is by flipping the signs. By flipping which electrode is positive and which electrode is negative, we can force the electrons to move when they normally wouldn't have. Because what we do is hook the positive end of the battery up to the anode, so we're flipping the sign, and we hook the negative end up to the cathode. What this does is it pushes your electrons from the anode, because at anode we have oxidation, and if you hook, the electrons are going to be attracted to the positive end of the battery. So the electrons move to the positive. They do. You have a voltage source, you hook a positive end up to the electrodes. It's like you are sucking the electrons out of the anode. You put the positive end there, the electrons say, hey, we're negative, let's go check out what that positive is. They get sucked out of the anode by force. And then you hook the negative end up to the cathode. So the electrons, they get sucked up to the battery, they hit the positive end of the battery, they move through the battery, and then they hit the negative end of the battery. And then you're going to get repulsion. So the electrons sort of get over to the negative side, say, hey, we don't want to be here because we've got the same charge. So then they get pushed into the cathode. And the figure on the next slide is going to show that. So differences, absolutely key differences here between the Voltaic cell and the electrolytic cell. In electrolysis, your signs have changed on your two electrodes. Your anode is your positive electrode, your cathode is your negative electrode. And again, so all set with that, just showing this, blowing up this picture. This is a different non-spontaneous reaction. In this reaction, just to point out what's going on, we're taking water and we're turning it into oxygen gas and hydrogen gas, which, you know, doesn't happen spontaneously on its own, which is a good thing. We don't want our water randomly turning into two highly flammable gases. Sorry, just go back. Positive end of the battery, I'm going to draw it nice and big. We hook it up to the anode so that the anode becomes positive. Negative end of the battery, we hook it up to the cathode. The cathode becomes negative. This is what forces this non-spontaneous reaction to occur. The electrons are pulled out of the anode because of this charge. They get sucked up. They wouldn't normally do that, but you hooked a positive up to that piece of metal, so the electrons are naturally going to be attracted to it and they're going to move out. And then the electrons kind of move through the battery, and then they get here and they encounter this negative, and now your electrons are pushed into the cathode. This is how we force redox reactions to happen. It truly is this idea of pull and push based on the charges in the battery. You hook the positive end up to the anode, the electrons are going to get sucked out due to electrostatic attraction and the voltage source, and then they get to the negative end of the battery, they're going to be pushed away due to electrostatic repulsion, negatives repelling one another. Anode is still oxidation. You are absolutely still losing electrons at the anode. Cathode is still reduction, still gaining electrons at the cathode. Electrons are still moving from the anode to the cathode, absolutely, but we have flipped the signs, and that's how we get this electrolytic non-spontaneous cell to work. Now, electrolysis and mass changes. The final, with electrolysis, this is very frequently used to generate metals. It's typically metals that you can't normally get on your own. This is how you could electroplate things in a metal. If you have any jewelry that's gold plated or silver plated or platinum plated, it was generated through electrolysis by coating the outside of an object in that metal. And so a calculation that we can do is figure out how long will it take this cell running to plate a certain amount of this metal onto an object. It doesn't have to be plating. It can also be used to just generate the metal, period. You want to get some gold and you have gold solution. Okay, run an electrolytic cell and you can generate some gold metal. You need the gold ions in solution to begin with. And the way it's done, it's essentially this absolutely crazy cracked out dimensional analysis problem, which is why I like it, because I like dimensional analysis. It's simply unit conversion, and as long as you're converting your units correctly, you know you're doing the problem correctly. So electrolysis and mass change, it really is just unit cancellation. That's all it is. No formulas, no nothing, just working with the units. But there are a few new units that we have to talk about in doing this type of problem. What's shown here on this slide is the outline for how we solve this type of problem. Typically, you will be given the amperage that was run through your electrolytic cell, I'm going to talk about what that means in a second, and the time that the cell ran. How long was your electrolytic cell running? So those are typically starting values. I will say that we can obviously flip this whole thing around and go in the opposite direction, which is what you're going to be doing on some of the homework, in which case this would be the current and amperage, current/time would be your end game rather than your beginning. But you take current and you take time, and from that you can turn that into coulombs via Faraday's constant. We're going to talk about that. And then through coulombs, we can turn that into moles of electrons. Again, that's Faraday's constant is what's going to link all this stuff together for us. Once we have moles of electrons, now we can look at our half reaction and see how do moles of electrons relate to moles of whatever metal or substance it is that we're interested in oxidizing or reducing. And then once we have moles of that substance, we can turn it into grams. So a few absolutely key things that we need to know before we do this dimensional analysis. Number one, amps. Current in amps is a unit that measures charge per time. And charge is coulombs and time is seconds. So putting this another way, putting this a simpler way, amps, which is abbreviated as capital A, is equal to coulombs, capital C, per second. This is on your reference table. This relationship right here, this is on your reference table. And if you have your reference tables out, if you don't have your reference tables out, please get them out. And I want you to find where this is, because this isn't as obvious as some of our other things. It's actually not written quite like this. Amps equals coulombs per second. It's written a different way. I equals Q over T. It says what everything means. I do believe it says what absolutely everything means, that, that amps is equal to coulombs per time in seconds, but it's sort of hidden a little bit. But knowing this relationship right here is critical for beginning this, because if you're given amps, the first thing that I'm going to have you do is to not write it as amps, to write it as coulombs per second, to understand that it is a conversion factor, and you're going to use it as a conversion factor. And we can go in the other way as well. Coulombs will be amps times time. But really it's this amps is equal to coulombs per second. We're going to use that the most. Now, Faraday's constant. How does Faraday's constant tie in with all this stuff? Faraday's constant is 96,500 coulombs per 1 mole of electrons, aka something that we can write in terms of dimensional analysis, coulombs per 1 mole of electrons. So hopefully you're kind of seeing that if we take the amps that are up here, coulombs per second, we can tie in here and we can cancel out coulombs. That's critical for us when we're doing these dimensional analysis problems. Then, through Faraday's constant, we now have moles of electrons. That's sort of the idea, that Faraday's constant can get us moles of electrons. And we can relate the moles of electrons to moles of whatever it is the problem is asking about through the coefficients. And then simply turn moles into grams. So the basic structure is you take your amps and you take your time. And you figure out how many coulombs do you have. Because time will cancel in amps, right? If you have a certain amount of time and it's running at a certain amperage, you can figure out how many coulombs have passed through the cell. What is the charge that has passed through the cell? Then you take Faraday's constant, which is coulombs per mole of electrons. You relate charge to how many moles of electrons must have passed through the cell. You relate moles of electrons to moles of your substance. You turn moles of your substance into grams of your substance, and you have at that point answered the question. So we're going to practice with this, because this is kind of, like I said, it's crazy cracked out dimensional analysis, but it truly is only dimensional analysis. It's not any formula. It's not anything other than that. It's just being able to work with the units. So, how much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amps is passed through the cell for 1.5 hours? So, first thing, hopefully your chemistry intuition is kind of telling you maybe we should write a reaction. And if we're looking at what we're starting with, it says how much calcium will be produced. That means that calcium is a product. And we're making it from the molten CaCl2. So that's a reactant. Well, we're only making calcium, not a calcium compound. It's calcium atoms on their own. So hopefully you can kind of guess that the other product must be chlorine gas. So we're going from calcium chloride solid to solid calcium metal plus chlorine gas. Now this is non-spontaneous because the metal and calcium and chlorine are much more energetically stable when they're bonded to one another rather than being separated. We want to separate this out into a half reaction because it is asking us about the calcium. So I'm going to write the calcium half reaction. This is Ca plus 2 electrons goes to Ca. And we're going to see why we need that in a little bit. So this is really describing what it is that's going on in our reaction. And now we can start looking at our numbers. Well, what numbers have they given us? 0.452 amps. And what I want you to do, as soon as you see a problem that has amps, I don't want you to write it as amps. I want you to immediately write it as 0.452, that's a 5, apologies, 0.452 coulombs per second, because that is what an amp is. That is the definition. So I want you to write it based on those units because it's going to help you with your unit conversion. So as soon as you see that amps, I want you to write it as 0.452 coulombs per second and think that immediately. We also have time, 1.5 hours. Now, the problem gives us two numbers, right? We have the 0.452 and we have the 1.5. So obviously we're going to start our dimensional analysis with one of those two numbers. We want to start with the number that only has one unit in it. You never start converting with a value that has multiple units like molarity. Molarity is moles per liter. You don't really start, if you're doing dimensional analysis, with the molarity. You'd start with either moles or volume. You wouldn't start with density. You'd start with either mass or volume. In this case, we don't want to start with the amperage. We want to start with the hours. So we're going to start our unit conversion with the hours. Now, looking at what it's asking, how much? So we're looking for amount of calcium. That's our end game. But we're going to start with the hours. Now, the first thing that we want to do, we want to start to turn this hours into coulombs because we've got seconds right there. But hours and seconds, they're not the same unit. So we're going to start by converting the hours into seconds. So 1 hour, 60 minutes, and then 1 minute, 60 seconds. What we're doing is turning our unit of time into the unit of time that is used in the problem in amps. Amps is coulombs per second, so I want to get the hours into seconds. Hours have canceled, minutes have canceled, now I'm at seconds. Now we're going to use our amperage. Our amperage says 4.452 coulombs per 1 second. This gets me to coulombs, which I need to do in this problem. Right, this has converted time into coulombs. Coulombs is about charge, measuring how much charge is passing through your electrolytic cell. So this is kind of a key critical point in solving this problem, knowing to use your amperage here. Now, if you have a look at what it says to do, once you get coulombs, the next thing to do is to turn it into moles of electrons, because while coulombs don't relate to the calcium, electrons do. So you want to turn coulombs into electrons. So coulombs are going to be on the bottom, moles of electrons are on the top. And this step right here, coulombs to moles of electrons, that's Faraday's constant. That's F. Faraday's constant is what relates moles of electrons to coulombs. And if you look at Faraday's constant, it's 96,500 coulombs per 1 mole of electrons. So Faraday's constant lets us go from the coulombs in our cell to moles of electrons in our cell. Now coulombs have canceled. Now we have moles of electrons. We don't want moles of electrons. I'm going back to this right here. We want the amount of calcium. But this is why we wrote this half reaction right here, because this half reaction right here tells us the relationship between moles of electrons and solid calcium. It says that we have 2 moles of electrons is capable of making 1 mole of Ca. And because this problem doesn't specify mass, we can actually leave it as moles of calcium and go through and calculate the answer. We turned time into coulombs. We turned coulombs into moles of electrons. We turned moles of electrons into moles of calcium. So go through and calculate this. 1.5 times 60 times 60 times 0.452 divided by 96,500 divided by 2. And hopefully when you do this math, you get 0.0126 moles of calcium. Now, if you wanted to, you could very easily turn this into grams of calcium. All you'd need is the gram formula mass of Ca. That's just straight from the periodic table. 1 mole, 40.1 grams. 0.507 grams of calcium. Electrolysis problems are nothing but cracked out dimensional analysis. That's really all they are. That's it. That's all they are. But they're brilliant because all they are dimensional analysis, just unit cancellation. Critical points, though, to working with it. Using your amperage as coulombs per second and using Faraday's constant, 1 mole of electrons per 96,500 coulombs. Those are the tricky points. If you can feel comfortable working with amps as coulombs per second and Faraday's constant as 96,500 coulombs per mole of electrons, you'll be fine in terms of doing the unit cancellation and solving this dimensional analysis. So we're going to do one more problem. And then you're going to have time to work on this. The last 2 questions on the homework are electrolysis problems, and some of them do have you going in the other direction, which we'll talk about a little bit after this question. So the last sample problem, number 5, calculate the mass of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. So similar idea. You do want to describe what's going on in terms of a chemical reaction. And we're starting with AlCl3, and we're turning it into Al. Right, we're producing aluminum. We're starting with the molten aluminum chloride. The other product is going to be chlorine gas. This is not balanced, so balancing it out, we're going to need a 2 here, we're going to need a 2 here, we're going to need a 3 here. Half reaction. We need to write the half reaction for the aluminum. Why do we need to write the half reaction for the aluminum? We have to know how moles of electrons fits in with that aluminum, because all the work with the amperage will get us moles of electrons. So we need to know what the relationship is between moles of electrons and moles of aluminum. So if we separate this out, at first you might write this. Right, that would be balancing it. Now this is the same thing if you reduce it down as simply Al plus 3 electrons yields Al. Right, that's the same, it's going to be the same relationship between the aluminum and the moles of electrons. So that's what we need. We need to see, this relationship right here. We have to see that. Then let's look at the numbers. Problem gives us time, so we have 1 hour. And it gives us amps, which Mrs. Julian is going to immediately write as coulombs per second, because that's what it is. That's what I want you to do. I want you to immediately write that as coulombs per second. Then we're going to start our dimensional analysis. We're going to start converting units. We want mass of Al. So we're looking for grams of Al. So we're going to take this thing to the bitter end. We're going to start with the time, because there's only 1 unit in it. We're not going to start with the coulombs per second because it's got 2 units in it. You always want to start with the thing that just has 1 unit. So 1 hour. I have to start by turning this into seconds because the units for time need to match, and right now they don't. So 1 hour, 60 minutes. 1 minute, 60 seconds. Dimensional analysis. Units on top and bottom. If they're both on the top and on the bottom, then the units cancels out. Now I have seconds on the top, so I want to put seconds on the bottom. What do I have that involves seconds? Amperage. 10 coulombs per 1 second. That's what that is saying. So this allows me to turn seconds into coulombs. Well, now I have coulombs. Well, that's great. Coulombs aren't related to my aluminum here, right? There's nothing here about coulombs, but I do have electrons. Coulombs are related to electrons. There's a relationship there. And that is Faraday's constant. Faraday's constant says that there are 96,500 coulombs in 1 mole of electrons. It's about measuring the charge on an electron. Okay, now I have moles of electrons. Now coulombs have canceled. I want mass of aluminum. So now I go up and I look at the relationship between electrons and aluminum, and I see that for every 3 moles of electrons, I get 1 mole of Al. You could also put 6 and 2. That would work. You're going to get the same answers. And then the very final step, because I'm not done yet, I have to turn moles of Al into grams of Al using the gram formula mass. Right, that's the very last step. And you have finished with your dimensional analysis, and that's just calculating 1 hour times 60 minutes times 60 seconds times 10 coulombs per 1 second divided by 96,500 divided by 3 moles of electrons per 1 mole of aluminum times 27 grams of aluminum. That is the math that you are doing. And I'm waiting because I'm hoping you're actually doing this math. And you should get 3.36 grams of aluminum. And that's it. All electrolysis problems are going to, basically what I'm showing you here is the longest possible electrolysis problem I could show you. You might only see certain portions of it. A question on the free response might only be asking, not necessarily top to bottom, but maybe just bits in the middle. And again, it's this crucial middle section that you need. That's really what you need to make sure you understand. That if you have time, you can relate it to coulombs using amperage. If you have coulombs, you can relate it to moles of electrons using Faraday's constant. If you can remember that, you'll be fine when you're working with this dimensional analysis, because it's just about getting units to cancel. Keep on converting stuff until you get the unit that you want. That's it. Now, if we're going in the opposite direction, maybe I give you mass and I ask about something like time, right? Maybe I start here and I ask about how long would it take. You just work backwards. Turns grams into moles, turns moles of substance into moles of electrons, turn moles of electrons into coulombs using Faraday's constant, turn coulombs, use coulombs to figure out amperage. I mean, the problem will probably give you amperage, and so what amps are coulombs per second. So if you have coulombs and you have amps, you can figure out time, right? Amperage is just coulombs per second. If I give you the coulombs, you can tell me the time based on that relationship. And that is what a few of the homework problems are like, sort of going in the opposite direction. But the key crucial unit conversion points, they're still the same. Okay, ladies and gentlemen, very exciting, because that's it. We're done with new material. No more new material before the exam. Ooh, that's crazy. That's absolutely very exciting. So use the remainder of class to work on the practice electrolysis problems 81 and 82 from the bookwork. We will go over all of these tomorrow in class in the double period, but I wanted to ensure that we got through the electrolysis so that you did have these notes. You will be getting the material for the Chapter 20 review tomorrow. And I do want to remind you that your equilibrium test corrections are due the day we get back from break. And that week that we get back from break, we are going to be taking a practice multiple choice exam. And yes, it is going to count as a test. I'm going to curve it, so it's going to be 5, 4, 3, 2, 1. But it will count as a test, so please be prepared for it. And it is all encompassing, right? It's a practice AP. It's an AP test. That's what you're going to be taking. So be aware that that is coming up. You'll get a few review materials tomorrow in class to help you get ready for that. And be good for the sub, because if not, I'll hear about it.